Welcome to EPG Pathshala in Computer Science. We are looking at a series of lectures on computer networks. So, we will be looking at the IPv6 protocol today. We have looked at IPv4 and the associated protocols in detail at the network layer. So, we will be looking at the version 6 of the IP protocol. So, we take a brief overview of that particular protocol. So, specifically we will look at the motivation for the V6 protocol. We will look at the various features of this protocol, the way the headers are organized and the way the addresses are organized, and how the version 4 to version 6 transition is planned. So, if you look at the initial motivation for IPv6, the basic motivation comes from the fact that the 32-bit addresses that we had, 32-bit address space that we had in IPv4 has been getting exhausted. Okay. So, since that is almost completely exhausted obviously, and there is a demand for many more addresses. So, naturally there was this drive for expanding the address space. So, that was one of the first motivations to go for another version of IP where you would have an expanded address space. That was the first motivation. An additional motivation was that with the increase in the traffic that we have, we definitely need to have very quick processing. So, if we could also make sure that when you are making a change, a version change, if you could also make sure that the header format and other things can be modified in an appropriate manner, so that it will help in terms of fast processing and forwarding of the data, that would also help. So, that was another additional motivation, and in addition to that, of course, there is always this need to support quality of service. So, that also has been included as part of the IP protocol. So, with these three kind of goals, the version 6 protocol was designed. Okay. So, shortage of address space and lack of quality service guarantee. So, these are the two things that we are trying to address. The work on IPv6 started quite a few years back, almost in the 1990s, and from 1995 there have been different proposals that have been looked at, and then now IPv6 has been standardized. Okay. So, the major features, if you look at of IPv6, you will find that there are a number of them that we need to understand. The first one, of course, is that it has an enlarged address space. Now, how enlarged is it? We had a 32-bit address space in IPv4. Now, it is a 128-bit address space, that address that you have in IPv6. So, which means you are talking about 2 to the power of 128 different addresses. Now, you can see that it is a very, very large number. Okay. Second thing is the address hierarchy uses an aggregation based mechanism. So, the way the addresses are laid out, they are done in such a manner that it becomes easy to do the aggregation. So, we remember that we had seen something like this when we talked about the CIDR addressing in IPv4. So, the same idea has been extended, and the addressing mechanism itself has been designed in such a manner that it becomes easy to do aggregation, and therefore, the backbone routing also will become more efficient. So, this is something which has been incorporated in IPv6. And the header format has been redesigned in such a manner that you have a fixed header format, so that it will help in processing and forwarding the packets faster. So, it gives you an efficient and extensible IP datagram structure, and there is better support for quality of service. We will see how that is done. There is support for authentication and security. And now, the IPsec protocol, which is for providing security, has been made mandatory in IPv6. So, you have support for authentication and security. There is also support for auto configuration. So, there is a stateless address auto configuration mechanism that has been supported, so it becomes easy to assign the addresses. Another very important aspect of IPv6 is that it supports fragmentation, but it is an end-to-end fragmentation that is supported, which means you do not have fragmentation at the routers or the intermediate routers, but fragmentation has to be taken care of at the ends. The advantage of this again is that your processing becomes faster. There is also explicit support for mobility. In fact, it becomes very easy to implement your mobile IP devices, and there is enhanced support for routing functionality, which including support for mobile hosts, for multicast. There is also another feature called Anycast. So, you have an Anycast address that can be specified, which basically means that you will route to any of a group of addresses. So, this can kind of be used to route to the best of several replicated servers. So, this is what you can do with Anycast addresses. So, these are the major features that we have of IPv6. Now, we will take a look at some of these things in detail. So, the IPv6 addresses we said are 128-bit addresses, and so that gives us an expanded addressing capability. So, there are more levels and more nodes can be supported. the idea followed is something very similar to CIDR, that is you have a classless addressing mechanism, so that it becomes easy to aggregate the addresses and it gives you flexibility in the aggregation of the addresses. The notation that is normally used, remember it is a 128-bit address that we have to specify. So, the 128-bit address is specified by means of what we call as a colon hex notation. So, you have these hex numbers, 16-bit hex numbers separated by colons. So, you will have 8 such, 8 into 16 is 128, right. So, each of these x's represent a 16-bit hex number and you specify the entire address as x colon something like that, okay, something like this. And if you have a contiguous set of zeros, that can also be compressed, you do not have to write down all the zeros, it can be compressed by putting 2 colons like this, okay. And there is also support for IPv6 compatible IPv4 addresses. So, where you have a leading set of zeros which is indicated by means of these 2 colons and then you have your typical IPv4 kind of an address. And the address assignment, you have support for both provider based and geographical address assignments. So, there is a lot of flexibility in the way the addresses can be done. Okay. Now, coming to the datagram format, we said that the format is a very simple format. So, if you look at the format, you can see that you have a version field and there is something called a traffic class field, then there is a flow label and then we have a payload length, then we have a next header, you have a hop limit, then there is a source address and the destination address. So, you can see that this is followed by either next headers and then followed by the data. Okay. So, overall you can see that this entire thing is just a 40 byte base header. So, all IPv6 datagrams have this 40 bytes base header. So, the new fields that you can see, version obviously refers to the fact that it will be version 6. Now, another new field that we have is a traffic class. Now, this traffic class, or it is referred to also as priority. Now, this is essentially to identify the class of service or the priority of the datagrams in the flow. Now, we also have something called a flow label. So, this is essentially to identify the datagrams which belong to the same flow. Now, this is obviously to support quality of service, because using a flow label you can identify those datagrams which belong to a particular flow, and using that you can provide certain types of service for that particular flow. Okay, it becomes easy to do that. Okay. Payload length, that is easy to understand, it just gives you the length of the payload including the other next headers, and then you have a next header field. Now, this next header is the one which will point to the next header if it is available, and if there is no other header, it just points, it identifies the upper layer protocol for data, that is whether it is TCP packet that is being carried or the UDP packet that is being carried in this IPv6 format. That information will be specified here. Whereas you would have had a protocol field in IPv4, so that is kind of merged with this next header field over here. So, there is a kind of an optimization that we have by using this next header field for 2 purposes like this. And then there is a hop limit, which is our TTL basically, similar to our TTL, and then of course you have the source address and the destination addresses. So, this is the IPv6 basic datagram format. So, this traffic class that we talked about, it is an 8-bit field, and again it is available for use by the originating nodes and or the forwarding routers to identify and distinguish between different classes or priorities. For example, it could be used as the code point in diffserv. Okay, that is a possibility. The general requirements with respect to the use of this traffic class field is that the service interface must provide means for the upper layer protocol to supply the value of the traffic class, and the value of the traffic class can be changed by the source, by the forwarder or the receiver. And an upper layer protocol therefore should not assume that the value of the traffic class in a packet has not been changed. Okay, it is possible, so it should be aware of that. Okay. Next is the flow label field that we have. Now, we said that this is related to a sequence of packets. So, whichever those packets need some special handling. So, the flow normally is identified by means of the source address, destination address plus the flow label, which means, so between a source and a destination pair, you could have multiple flows, and each of those flows could have different labels. So, you could have different treatments for different flows, even if they are between the same 2 pairs of nodes. Okay. And the router basically treats this flow with different, can provide different sharing attributes. For example, the path may be shared, or resource allocation, discard requirements, accounting, security, all these are various things, treatments that could be given to the flow, which will be based on the flow label. So, you could aggregate different flow labels to provide similar kind of treatment and so on, right. So, those are the things that we have. And so, it may also treat flows differently. For instance, Buffer sizes could vary for different flows, different forwarding experience can be provided to different flows. So, essentially different quality of service. So, basically there is an alternative to including all the information in every header, because all the information that you want for the quality of service related information is available as part of this flow label, which is there right at the top in the IPv6 header. Okay. So, the payload length that we have, as I said, the length, it is a 16-bit unsigned integer, and basically it counts the rest of the packet following the IPv6 header, and which means that extension headers, if they are there, they are also included in the length count. So, that is one thing to note as about the length field here. Now, if you compare the V4 and the V6 formats, okay, just a comparison of these two to understand how the V6 has evolved. First thing is that we have a fixed length 40-byte header in IPv6, so which gives us simplified processing and reduces the bandwidth cost. Okay. And all other information that you want are all specified by means of extension headers. And what is very interesting about most of the extension headers is that most of them are a fixed length, and all these extension headers are in a fixed order, which again helps to make the processing faster, because remember, if they are in a fixed order, it becomes easy for you to process one after the other. So, something is not there, you know exactly which is the one that is missing, right, and it is not even mandatory that all of them should be present. So depending on the header that is present, depending on the order, the processing can be done more efficiently. So, we have extension headers to support fragmentation, to support source routing, to support authentication and security, and for other options as well. Okay. So, we will take a look at these extension headers now. So, if you look at the various changes that we have, this is our IPv4 packet format, and this is the V6 packet format. So, a number of fields have been removed. Okay. So, what is it that has been removed? You do not have an ID, flags, flag offset, that is the ones we use for fragmentation, they are no longer part of the main header. There is no TOS field, there is no H length, header length field, and there is no header checksum. And the ones that have been changed, total length, that is now changed to a complete payload length, okay, and protocol field that we had has been now changed to next header field, and the TTL is now changed to hop limit. Okay. And there are two new things that have been added, one is the traffic class and the other is the flow label. So, these two things that we have here. Okay. And our addresses have been expanded from 32 to 128 bits. So, something has been changed, something has been removed, something has been added, and something has been expanded. So, that is the overall change from V4 to V6. So, other changes that we talked about. So, checksum, again see that checksum has been removed from the header, so that you do not have to do this processing of checksum at every step. So, we are saving time that, in terms of the processing that needs to be done at every hop. Okay. And the options field, again it is allowed, but it is outside of the header, so which is indicated by the next header field. So, that again helps to improve the efficiency of processing. So, fragmentation, I said, is not allowed at the router. So, again we are trying to reduce the amount of time taken for processing the packets. And then there is also a new version of ICMP that has been supported, ICMP v6, which is the companion protocol for IPv6. Now, this has support for some additional message types and certain other functions which are required for IPv6 to function efficiently. So, IPv6 plus ICMP v6 gives us a good combination that can be used for very efficient processing. So, v6 for instance has an additional message type called packet too big. So, if you have a very big packet that is being sent, so which means basically it needs to be fragmented, but of course we do not have support for fragmentation here. So, the source will have to fragment it and send the packet. So you have a message like that. Then of course there are multicast group management functions that is also supported with the ICMP v6 protocol. Okay. So, if you look at the extension headers, as we said, we have an extension header for routing. Okay. So, like IPv4, you can specify some kind of a source routing option, that is you can either specify loose source routing or strict source routing. So, normally it is a list of routers that needs to be visited. So, that can be specified as part of the routing extension header. Then of course, we said we have an extension header for doing fragmentation and reassembly. Remember, we said fragmentation and reassembly is done, fragmentation is done by the source, reassembly is done by the destination. No fragmentation takes place at the routers, but we have a header. But if we had a large packet that was sent by the source, which IPv6 had to fragment, it would fragment it and it will put the information in the fragmentation headers and send them as fragments right through the network. Okay. So, we will look at how that is done. Okay. Then as we said, there is a extension header for integrity, authentication and security. Basically authentication, integrity and security are provided. Okay. And then there is encapsulation support, so confidentiality. Basically you can see that both these things are supported by allowing IPsec to be implemented fully. So you can have IPsec support along with IPv6, so that provides all the security requirements. Okay. And then there is something called a hop by hop option. These are special options that require hop by hop processing. Now you will find that most of the extension headers except one or two will not be processed at every router. So this hop by hop option is one of that kind, the one that needs to be processed at every hop, so that some special information may be specified in that. Similarly, you have something called destination options. Again, this is optional information. This is to be examined by the destination node. Okay, so these are the types of extension headers that we have. So what will this header look like basically? So if there is no extension header, which means there is just data being carried in that IPv6 packet. So you will just have the IPv6 40 byte header, and the next header field in that will indicate that it is a TCP packet that is being carried. That is, the upper layer protocol is TCP, and this TCP header and data will be the datagram that is carried in this. Okay. Now if you had one routing header, let us say, that was present, so then your IPv6 header, the next header will say it is a routing header. So it will be immediately followed by the routing header here, so which will say next header is TCP, because what is inside this is a TCP packet. So you will have this part specified here. Okay. Now if you had a routing header followed by a fragment header, what will it look like? You can see that the IPv6 next header will point routing, so that will be followed by the routing header. Routing header will have its next header field specified as fragmentation header. So the fragmentation header will follow that, and in that the next header will point to TCP, indicating that it is TCP packet that is carried in this. So this is basically the stacking of the extension header. So this is basically how it gets done. So the IPv6 extension header not processed by intermediate routers except the hop by hop option header. Okay. And they are processed strictly in order. So this again is to improve efficiency of processing, as we said. And each extension header occurs at most once, except destination options header, which occurs at most twice. So this is basically what you expect to find in the IPv6 list of headers. And we said there is a fixed order, so this is the order that is followed. So you will have the basic IPv6 header, so that would be followed by a hop by hop options, that is followed by routing header, followed by fragment header, then authentication header, then the encapsulation security payload header, destination options, then mobility header, and then the actual header of the packet address. Or if you had no next header, then that would point to a value of null, and then your upper layer information will be specified in this. Okay, so this will be the last one. So if there are none of the options specified, your basic IPv6 header will be pointing to this upper layer, as we saw in that example. Okay, so that is basically what you have. So the PDU structure therefore will look like this. So you have your application data, TCP header added to it, then the different headers, so destination options header, fragment header, routing header, hop by hop options header, and then the IPv6 header, right. So this part, the IPv6 header part, this is the mandatory IPv6 header, all these are optional, and that is followed by the actual data, the packet body. The hop by hop options, we said this is something which has to be examined by every router. So normally this is used to specify some specific discard and forward policies or handling mechanisms. So there are different options that we have. We talk about a padding option, pad 1, pad n are two different options that we have. We will not go into the details of these. There is one which can be used to specify that it is a jumbo payload, which means that it is a large payload, and there are also router alerts which can be specified as part of these options. So these are options which will be processed at every router. Okay. So the routing header, as we said, this is used to specify a list of one or more intermediate nodes that it has to visit. So the header will include next header, header extension length, routing type. For instance, if it is type 0, it indicates it is source routing, and then the number of segments left. Okay, we will just take an example of this. So for instance, this is what you will have. Source, let us say we are going through 1, 2, 3 different routers here. So the packet will specify the source is A, destination is R1, okay, and how many more are left? There are 3 more segments or 3 more routers that need to be visited. Okay, so R2, R3, and then you will read the destination. So this is the information that you have. This left right? That gives you the number of segments left, number of segments that you need, number of hops that you still need to go through, okay. And so when it goes to R1, when it is forwarded by R1, when R1 processes it, now R1 has already been processed, right. So now what will happen now? The destination will be replaced with R2 because now it has to go to R2, and left will be changed to 2. So you have your R1 replacing this, okay. So now when it goes to the next one R2, R2 will process this, it will find it has come to R2. So it will change, it will look at the next header is the one that is to be processed is R3. So it changes the destination value to R3 and then forwards it to R3, okay. So at R3 it will see that R1, R2, R3 have already been visited. So what is left is only the final destination has to be reached. So left is 0, it will go to the destination, okay. So by using these fields, you can see how the routers will be able to forward the packet using this source routing option, okay. This is basically how it works. It's very similar to what happens in IPv4 as well, but you can see that it is done in a very efficient manner. So the fragmentation header, we said that the fragmentation will be performed only by the source, no fragmentation at the routers. So what does the fragmentation header look like? This is, you can see this here. So you have the next header, then there is some reserved field, and then you have a fragment offset, and there is a R field, and there is a M. Remember our M and fragment offset and identifier. These are very similar to what we have in IPv4. You have the more bit, you have the fragment offset, and you have the identifier field. So it's pretty much the same fields that we have here. So the offset is an 8-bit unsigned integer, and the offset of the data following the header relative to the start of the fragmentable part of the original packet. That is what is specified over here. Now we talk about a fragmentable part and an unfragmentable part. Now what is the unfragmentable part? The IPv6 header itself is obviously unfragmentable. The IPv6 header plus any extension headers that must be processed by nodes en route. So those have to be left as an unfragmentable part, whereas the rest of the things that can be fragmented, okay. So this is that is what will be specified by the fragment offset, okay. So if this is my original packet which has IPv6 followed by so much of data, so the fragments will be IPv6 followed by a fragment header, and then you will have your fragment 1 data. So then next fragment will have a fragment header, fragment 2 data, fragment 3 data, and so on, okay. Now one interesting fact to note about the fragmentation part is that, remember, if fragmentation is supported only by the source and not by the routers, then how is it that the source will get to know that this is the size of the fragments that it has to use? So what the source would normally do for that is that when it sends out a packet, if a particular router is not able to process it, it will send back an ICMP message saying that it is too big, that the packet is too big for it to process. In that, the MTU of that particular router will also be specified. So once that is specified, now IPv6, the source can make use of that MTU to send the fragment. So it can restrict the fragment size to that MTU and send it, okay. This is what it will do. So it will have to do it will have to identify, or it has to discover what the maximum transmission unit is. So normally we talk about something called a path MTU discovery, okay. So what IPv6 suggests is that the MTU of every link must be greater than or equal to 1280 bytes, okay. So the so which means minimum MTU is 1280. So you can use a path MTU discovery to discover MTUs which are greater than 1280. So if it's greater than 1280, obviously you can send larger sized packets, right. So that is what it will do. So therefore what we have is the requirement for a node is that it should accept a fragmented packet that is as large as 1500 octets. So these are some of the guidelines that are given by IPv6, okay. And reassembly gets done only at the destination. So the unassembled part, unfragmentable part of the reassembled packet, okay, which will consist of all headers up to but not including the fragment header, right, that is the unfragmentable part, okay. So that is taken, and the next header field of the last header of the unfragmentable part, okay, that is obtained from the next header field of the first fragment's fragment header, okay. So the first fragment's fragment header is the one that will give us that information, okay. And the payload length of the reassembled packet is computed from the length of the unfragmentable part and the length and offset of the last segment. So that will give us this information. So this is basically how the reassembly part gets done. So this gives us an idea of how the reassembly is done in an efficient manner, okay. Now coming to the V6 addressing mechanism, there are three categories. We talk about unicast, multicast and anycast. The notation, as we said earlier, is a 16-bit hex separated by colons given like this, and whenever we have consecutive zeros, it can be replaced by a double colon, okay, as shown over here. Okay, this is the notation. And in IPv6 addressing, what we need to note is that the addresses are assigned to interfaces, not to hosts. So an interface could have multiple addresses, okay, and addresses have scope. That you could have a link local address, you could have a site local address, you could have a unique local address or a global address. Okay, so you have different scopes for the different addresses, and the scope identifier is normally given by means of the prefix of the address. So by looking at the prefix, you will be able to identify what kind of address it is. Okay, so the representation of the addresses that we just talked about this. Okay, and so the types of addresses that we have. So we have, as we said, we have something called IPv4 compatible addresses. Now the V4 compatible addresses are provided in order to facilitate the transition between V4 and V6. So here what you have is the initial first 96 bits, initial 96 bits are zeros, followed by the 32-bit IPv4 address, that gives us our 128-bit address. Okay. Global unicast has a prefix starting with 001. Link local unicast, this link local unicast indicates that whatever unicast packets are sent, they are sent only with respect to that particular link. It's local to that particular link. Okay. You have a site local unicast, which means it is restricted to a particular site, and then we have multicast. Okay. All other prefixes are reserved, and anycast addresses that we talked about, they are allocated from the unicast prefixes. Okay. So the global unicast addresses, we said that it is typically a hierarchically structured value which can be assigned to a site or to a cluster of subnets or links. Okay. So you have a global routing prefix, okay, which is based on the public topology, 48 bits, and then you have a subnet ID and then the interface ID. Okay. So the subnet ID will be an identifier of a subnet within the site, and the interface ID, this is the identity of the actual interface card that you have. Okay. So the interface ID is normally constructed in what is called as a modified extended unique identifier format, which is an IEEE standard. So this EUI standard gives us guidelines for converting your 48-bit Ethernet address, for instance, to a 64-bit interface identifier. Okay. Before that, we will look at the global unicast address, how the aggregation is supported. So you have this 3-bit prefix, and then we have TLA ID. Now this is the top level aggregation identifier, and then which can be 13 bits. Then there is a reserved field, and then there is an NLA, which is the next level aggregation identifier, and then you have a site level aggregation identifier, and then the interface ID. So you can see that there are different levels at which you can do the aggregation. So that helps. So you can have, for instance, current policy is that registry, you have 23 bits to identify registry, ISP can be identified using 35 bits, site can be identified using 48 bits, /48, and so on. So there are different ways in which you can do the aggregation. Okay. So this EUI 64 that we talked about extending your interface ID to 64 bits. So for a 48-bit MAC address, what is normally done is that it's basically split into two 24 bits, and between the third and fourth bytes, to say, you have a particular pattern that is inserted, and then there is something called a universal or local bit, which is there in the second lower order bit of the first byte, that is complemented. Okay. So you can work this out and see how the addresses basically get assigned. Okay. The only problem that we have with this kind of addressing scheme is that since the host address is specified as such, a host can be traced from the IPv6 address. So that is one point to note. Okay. Now we talked about site local addresses. Site local addresses are meaningful only in a single site zone, and they may be reused in other sites. So this is equivalent to the IPv4 private address space. So their addresses are not automatically configured, they have to be assigned. So there is a particular prefix that we use for the FEC0 is the prefix used, and this is the kind of structure that we have for that. Then we have link local addresses. So here these are addresses used for auto configuration when no routers are present, and so we also have a mechanism called neighbor discovery process that is supported along with IPv6, so which is again used for automatic configuration. So an IPv6 router will never forward a link local traffic beyond that particular link. So again you have a prefix FE80, unique prefix, which identifies that it is a link local address. So these are addresses that will be used when you want to identify your link neighbors on your link and so on, okay, or the router to which your link is connected, right, so that you can identify the router to which you need to send your packet. So those things are done with the help of the link local address. And then there are some special IPv6 addresses. We have the loopback address, okay, and we have IPv4 compatible addresses, so which are used by dual stack nodes, that is nodes which run both the IPv4 and IPv6 protocols. So in this case, the IPv6 traffic is automatically encapsulated with an IPv4 header and sent to the destination using the v4 infrastructure. So that is how we use the IPv4 compatible addresses. Then you have an IPv4 mapped IPv6 address. So this is to represent an IPv4 only node to an IPv6 node. Okay. So this only uses a single listening socket to handle connections from both v4 and v6, and this address will never be used as a IPv6 source or destination address, okay, and it is not very frequently implemented. Okay. So these are the multicast addresses. So you have the all ones indicating it is a multicast address, then there is a flag. Then there is a scope which specifies whether the multicast group is node local, link local, site local, organization or global. Okay, and then there are these other fields which gives us the length of the network prefix, the prefix to be used, and then a group ID and so on. So if you look at auto configuration, which is another important aspect of IPv6. So there are just as we have bootp and DHCP in IPv4, we have a DHCP v6 which can be used along with IPv6. There are two methods that are used. One is a stateless method and the other is a stateful method. The stateless method, the system uses link local address as source and multicasts to the all routers on this link. So now the router which is there will reply to this message and it will provide all the needed prefix information. So all the prefixes will have obviously an associated lifetime, so they will expire after that, so which means periodically you need to get this information. So the system can use the link local addresses permanently also if there is no router. So this is how the stateless configuration is done. The stateful configuration is done when you have a DHCP server. So here what happens is that in the stateless option anyone can connect. So in the stateful option what happens is that the router will ask the new system to go to the DHCP server, okay, by setting a managed configuration bit. Now the system will now multicast a message to all DHCP servers, and the DHCP server which is present on that network, it will respond and assign the address to this. It gives all the information. Now talking about a transition from IPv4 to IPv6, not all the routers can be upgraded simultaneously. We know that obviously, right? There is nothing like one flag day where we say that okay, all the nodes will move from v4 to v6. So the transition has been planned in an incremental manner, right, and the whole thing has been designed with this transition in mind. So what are the options that we have for transition? There are basically three options. You have a dual stack option, that is you will have devices where the v4 and v6 will coexist on one device. So you will be able to work with both v4 network as well as a v6 network. And then there are tunnels that have been used. Remember we already talked about tunneling, we know what tunneling means. Tunneling essentially is that you can take a v6 packet and tunnel it across v4 networks. You can manually configure the tunnel or it could also be an automatically configured tunnel. And then there are also translators which are IPv6 only devices which will communicate with an IPv4 only device. Okay. So dual stack and tunnels are the commonly used ones. So for a tunnel to operate, what happens is that you take the IPv6 datagram is taken and put as the payload of a IPv4 datagram. So you will have a datagram within a datagram, which is what is basically tunneling. Okay. So if you are sending, if I have two IPv6 networks here, B and E are IPv6 routers connected by means an IPv4 router in between. So what we will have is a tunnel is connected, is constructed between this B and E. So what will happen here is, so when a packet comes in A to B, it is an IPv6 packet. So that will be sent out from B to C as a tunnel packet, that is you will have a v6 inside v4. So what goes from B to C to D is a v4, and when it goes from D to E, you can see that the source will be B, destination will be E, okay, and this is a v6 inside v4. Now E will remove that the outer header that you have and send out the v6 packet to F. So this is basically how the tunneling gets done. Okay. So to summarize, we have looked at the IPv6 protocol, which is a new protocol, which is built basically on the experiences learned from IPv4. It has new features, large address space, efficient header processing, auto configuration and so on. But it is also old in the sense that it is still IP and it is built on a solid base and started in 1995. So, a lot of implementations and tests have been done, and we are already on this march towards IPv6. Many of our networks have now started getting converted to IPv6. So, that is what we need to be looking forward to. Thank you.